In this video, we want to introduce the concept of convolution and then illustrate the concept with a specific example. So suppose we have two functions. They're both functions of t, f of t and g of t. And when we say taking the convolution of the two functions, what that entails is taking an integral. But inside of the integral, we're treating these not as functions of t anymore. We're changing the t to an x. So instead of being f of t, it's f of x. But for the function that appears on the right side of the star, it's not g of x, but g of t minus x dx. So here in the integral, x is the variable, t is just being treated like it's a constant. And this seems like kind of a strange thing to do. This actually has a physical meaning. We're not going to explore that in this video. In this video, we're just going to lay out what the definition is and kind of blindly follow the formula to get a feel as to how it works. Notice though that when we integrate this, this will give us a function of t. We'll have a function of x, but then x goes from 0 to t, so this will give us some function of t. But again, here we have functions of t. Inside the integral, we write them as functions of x. And for the one that's on the right-hand side, it's t minus x dx, where t is now just being treated as if it's a constant. Now, what happens if we write these in reverse order? G of t, f of t. Well, we follow the same formula. Instead of being a function of t, this is a function of x. And instead of this being a function of t, it's a function of t minus x dx. So notice that if you write them in different order, in other words, instead of having f of t, g of t, if you write it like this, this is going to give you a different integral expression following the same set of rules. And x goes again from 0 to t. However, this does equal this, or this integral expression does equal this integral expression. In a few moments, we'll demonstrate that with a specific example. The reason why convolution is important in the study of differential equations is because of how it relates to the Laplace transform. If we have our two functions again, f of t and g of t, and they each have a corresponding Laplace transform, if I take their convolution and then take the Laplace transform of that expression, that's the same thing as if I took the Laplace transform of f of t and multiplied it by the Laplace transform of g of t. And we will prove this in a future video, this particular equation. If we take the inverse Laplace transform of each side of this expression, here we will have inverse of this, and then that will just be the convolution, written like this, or we can write it in this order. So if we have two Laplace transforms, we multiply them together, take their inverse Laplace transform, that does not equal f of t times g of t, it's equal to the convolution of f of t and g of t, either written in this order or in this order. Again, we won't demonstrate it, we will prove this in a future video. What we want to do in this video is demonstrate that this equals this, or this integral expression is the same as this integral expression. We'll demonstrate it with a specific example. Here. So we have t convoluted with 1/2 the sine of 2t. Here we have then reversed their order. So let's go ahead and write each of these in terms of its respective integral, just kind of blindly following our formula here. F of t inside the integral becomes f of x. What is f of t? It's just simply t. So inside the integral is just going to be x. And then here we can take the 1/2 to the outside. The sine of 2t, that's our g of t. Inside of the integral, it's t minus x. So here we will have the sine of 2 times t minus x dx. And the limits are x goes from 0 up to x equals t. So inside of the integral, these are no longer functions of t, they're functions of x, and the one on the right side of the star is t minus x. Now t is just being treated as if it's a constant. On this side, this will equal 1/2 can be on the outside of the integral. And again, f of t becomes f of x. So instead of the sine of 2t, that's the sine of 2x. G of t becomes g of t minus x. G of t here is just t, so this is going to be t minus x dx. Again, that's just blindly following our definition. And the limits are x equals 0 to x equals t. And we want to show then that these two integrals are in fact equal to each other. So let's start with this one first. We have 1/2 the integral of x times the sine of 2 times t minus x dx. X goes from 0 to x equals t. We may have to integrate this by parts, but let's do a substitution here first. Let's say let u equal 2 times t minus 2 times x. And remember again, inside the integral, the t is just being treated as if it's a constant. So du will equal minus 2 dx, or dx. That's minus 1/2 du. Now here we have x. If we solve that for x, we have x equals t minus 1/2 u. So let's put our substitutions inside of the integral. We have 1/2 x is this, t minus 1/2 u times the sine, and this is u. And dx, that's minus 1/2 du. Then minus 1/2 times 1/2. That will give us minus 1/4 on the outside. We will have different limits here, but let's not worry about these. Let's see if we can solve the integral. Then we'll put our substitution in. Then at that point we'll worry about the limits on x. So here's the integral. We can multiply it out. This will equal minus 1/4 the integral of t times the sine of u. We're treating t like a constant, so that can come to the outside, times the sine of u du, and then multiplying across here we'll have plus 1/8 the integral of u times the sine of u. And again, we'll get expressions here, substitute what u really is, then we'll worry about the limits on x at that point. The integral of the sine of u, that's minus the cosine of u. Here we have a minus sign out here, so this will give us t over 4 times the cosine of u. And then this integral, u times the sine of u, that's all set up to integrate by parts. Remember that from elementary calculus. When we do that, we have plus 1/8 this just gives us minus the cosine of u, the minus sign, so that's t over 4, the cosine of u. Integrate by parts here, and we have 1/8 the sine of u minus u cosine of u. And now we had to remember that u is equal to this expression involving x, and x has these limits, goes from 0 to t. So let's put all that in. This equals t over 4 times the cosine of 2t minus x. X goes from 0 to x equals t. Then we have plus 1/8 the sine of u, that's 2 times t minus x. X goes from 0 to x equals t. And then we have this expression, minus 1/8, let's put it out here, times u. U is 2 times t minus x. We'll have 2 times t minus x times the cosine of t minus x. Okay. Minus 1/8 times u. U is 2 times t minus x times the cosine of u. That's t minus x. X has the limits going from 0 to t, and this will be 1/4. So what we have then is this integral is equal to this term plus this term minus this term. So let's go ahead then and make some room, and we'll write this at the top and put in these expressions then and see what we get as to what kind of expression this integral finally gives us. So we had to remember, write this down, write this down, and write this down. We're going to need these three terms. So this is equal to t over 4 times the cosine of 2t minus x. X goes from 0 to t plus 1/8 the sine of 2t minus x. X goes from 0 to t, then we have minus 1/4 t minus x times the cosine of 2t minus x with the same limits. Let's see if we can get all this together. Okay, this plus this minus this is that integral right there. Let's see. Here we have t over 4 times the cosine of this with these limits. Over here, we're going to have minus 1/4. It looks like we have some cancellations. Let's go ahead and put our limits in and see what we get in the end. So this will equal t over 4 times x equals t, x equals 0. So when we have x equals t, we have t minus t, that's 0. So the cosine of 0 minus x equals 0, that's going to be the cosine of 2t. Then here we'll have plus 1/8 times the sine, x equals t, t minus t is 0, the sine of 0, minus x equals 0, that'll be the sine of 2t. Then we have minus 1/4 times x equals t. When x equals t, that's going to be 0. Minus x is 0. Here we'll have t times the cosine of x is 0, 2t. So here's our expression. This is 1 times t over 4, so that equals t over 4. Then here we have minus t over 4 times the cosine of 2t. Here we'll have plus t over 4 times the cosine of 2t. Those terms cancel. This is 0, so you have minus 1/8 times the sine of 2t. So this integral equals t over 4 minus 1/8 times the sine of 2t. So where we're at right now with our problem is we have shown this convolution, which is equal to that integral, gives us this function of t, t over 4 minus 1/8 times the sine of 2t. Again, we obtain that just by blindly following our formula that we showed at the beginning of the video. Now what we want to show is that this integral should give this same expression, and we will do that in the second half of the video. So come back and join the second half. Let's take this integral and let's see if in fact it does give us that expression. A reminder that the playlist for the videos on differential equations and all the videos, in fact, is at the website digital-university.org.